Okay, so we've got this last example for this particular type, and it starts with having to show something, and then you'll notice in the second part it says hence the sum of the series. It's a clue. Okay, you can see that if it has that two part and the second is hence, you know that the first part is critical. It has an essential part to being able to do the next. Now if for some reason you can't show that, you can at least use the result that's there for answering the next part of the question. Okay, so let's look at how we can show that first part. So we're going to work through that. Show that r times r factorial equals r plus 1 all factorial minus r factorial. So I'm just writing that out again. Okay, the best way to go about doing these is to use this right hand side, left hand side. It's the neatest, most elegant way to show this kind of proof. So put RHS for right hand side. Okay, it is equal to r plus 1 all factorial minus r factorial. Now that to work from there, that's the same as if we were to go r plus 1 times r factorial. Now we know that because, well, say 4 factorial, that is equal to 4 times 3 times 2 times 1. So we could also write that in as 4 times 3 factorial. And so that's all we've got here. R plus 1 factorial is r plus 1 times 1 less than that, which is r factorial. And so continuing on there, minus r factorial. And we can see then we've got a common factor of r factorial. Take that out the front. R factorial times r plus 1 minus 1, and if we were to simplify that, that becomes r factorial times, well, plus 1 minus 1 cancel, we're left with just r. Okay, and then that we can see is equal to the left hand side. And so then it's proven. That's what we needed to do. So QED to show that we've proven what we were required to prove. So that's the first part. Okay, so the second part is to sum the series 1 times 1 factorial plus 2 times 2 factorial, etc. to n terms. And we can, if we have a look at that, we can see that that's the same as the left hand side of the first part of our question. So we're going to let Sn, the sum to n terms, equal our series 1 times 1 factorial plus 2 times 2 factorial, and continue that on, 3 times 3 factorial, until we get to the end. That's going to be then n times n factorial. Okay, now what can we write that then? Well, that's the same as the sum to n terms from r equals 1 of r times r factorial, which we could also say is equal to, because of the first part, sum to n terms of r equals 1 of r plus 1 factorial minus r factorial. Now we're going to see how that is easier to work through and the best way to work through summing this series. Straight away we're going to let UR equal R plus 1 factorial minus R factorial. Now what we can do here straight away is to let that be a difference, VR minus VR minus 1, where VR is equal to R plus 1 factorial. Okay, sometimes it's just there and we can utilize this idea of VR minus VR minus 1 or whatever it happens to be. Okay, we could have equally have made it equal to VR plus 1 minus VR. That would have worked as well. Okay, but let's continue with what we've got here. That means that Sn, the sum to n terms, which is U1 plus U2 all the way to UN, and we can substitute, so that's V1 minus V0 plus V2 minus V1 Okay, we can see that there's going to be some cancelling. The V1 cancels with V1 here, so the first with the last of the next. V0 will not cancel, okay, and V2 cancels, and we'll see that V3 will also cancel with the next one. What we'll find is that Vn will not cancel, but Vn minus 1 will. Okay, so that means we'll be left with V minus V0 plus Vn, or it might be best to write it as Vn minus V0, and we can substitute that in. Okay, so it's going to be n plus 1 factorial minus 0 plus 1 factorial. N plus 1 factorial minus 1 factorial, which is 1. And that's our result.